scientific process as a unifying thread to make connections in chemistry. In parts 1 through 4, we discussed in detail major activities 1 through 3 of the scientific process, their tools, and the corresponding results. In this part, we will look into major activity 4, its tools, and the corresponding results. We will also discuss 4 major learning aids that are very helpful to students in their learning process. The fourth and last major activity of the scientific process is describing or communicating knowledge in a proper and an efficient way. The knowledge in question may be empirical or theoretical in nature. Of course, as was mentioned at the beginning of part 1, although listed here as the last major activity, it doesn't mean that in practice it is always the last one that scientists resort to. At each and every stage during each of the first 3 major activities, they engage themselves in this major activity as and when the need arises. There are 2 tools used for this purpose. The first tool to describe or communicate knowledge correctly is to invent special language that is as precise as possible. The corresponding result is special scientific terms, or for short, special terms. There are many special terms used in chemistry. A very small fraction of them is listed here. It is important for the students to know the precise meaning or definition of each term so that they can exactly follow what is communicated to them, or they can exactly communicate to others what they want to convey, especially on the exams. It is important to keep in mind that as time passes by, some terms become misnomers, namely incorrect or unsuitable terms. But due to practical limitations, we continue to use them, assigning new meanings to them. For example, Lavoisier thought that the new element he discovered in 1777, namely oxygen, was an essential constituent of acids. Oxy refers to acid and gen to generator or producer. Although this is correct with respect to all oxyacids such as nitric acid, sulfuric acid, etc., it is not correct with respect to hydrochloric acid, hydrobromic acid, etc. Therefore, oxygen is a misnomer now. Heat flow and work flow happen to be misnomers also. In 1783, Lavoisier replaced the then prevalent phlogiston theory with caloric theory, as the former did not explain the facts he had discovered. He postulated heat to be a substance called caloric and imagined it to flow from a hot object to a cold one, similar to the flow of water from a higher altitude to a lower one. Hence, the term heat flow used often. Less commonly, work flow is also used. But As per thermodynamic theory, which replaced caloric theory, as was mentioned in part 3, nothing possesses heat or work, as either is not a state function and everything possesses energy which can flow from one substance to another, either as heat or as work. Heat and work are path functions. According to statistical thermodynamic theory, either is just an agent or a mechanism that allows us to change the amount of internal energy possessed by systems. As per the first law of thermo, change in U is equal to Q plus W. By definition, U is the total energy of all the particles in the system. That is, U equals sigma Ni times Ei. Therefore, there are two ways in which U can be changed. One, by changing Ni's, keeping Ei's constant, and two, by changing Ei's, keeping Ni's constant. As per statistical thermodynamic theory, delta U equals sigma Ei times delta Ni plus sigma Ni times delta Ei, where the first term represents Q and the second W. Next, we will see the interpretation of these two terms. The mechanism of heat involves particles getting excited or de-excited among their allowed energy levels whose energies stay constant. This can happen through collisions among randomly moving particles, as in the case of energy flow from a hot object in which de-excitation occurs, leading to a decrease in the vigorousness of random motion of particles, to a cold object in which excitation occurs, leading to an increase in the vigorousness of random motion of particles. Or it can happen through absorption of energy, as in the case of a microwave oven and an electric stove, increasing the vigorousness of random motion of particles, or through emission of radiation, as in the case of the cooling of a hot metal, decreasing the vigorousness of random motion of atoms. The mechanism of work involves a change in the values of allowed energies of particles with the population of the energy levels staying constant. It is associated with a unidirectional motion of particles as opposed to their random motion in the case of heat. Mechanical work occurs during expansion or compression of gases when the particles of the gas exhibit a unidirectional motion. Electrical work occurs during conduction of electrons through a metal or of ions in an electrolyte solution when the electrons or ions exhibit a unidirectional motion. Therefore, heat flow and work flow are misnomers now. The correct term is energy flow as heat or as work. The second tool used for efficiently describing or communicating knowledge is inventing ways of communication that are as concise as possible. The corresponding result is what I refer to as special scientific representations or simply special representations. When the description is compressed in the form of a special representation, a safety measure becomes essential in order to ensure proper and uniform communication. Therefore, certain relevant rules are constructed. It is important that students know these rules and follow them strictly. For example, the most fundamental special representation in chemistry is the symbol used for each element and the corresponding atom. The specific rules that ought to be followed are listed here. The danger of not following them is clearly illustrated by the symbol for cobalt, which is uppercase C followed by lowercase o, and the formula for carbon monoxide, which is uppercase C followed by uppercase O. Another example of special representation is chemical equation. The corresponding rules are listed here. It is critical to follow these rules. In the case of a verbal equation, the names of reactants and products are used, whereas in the case of a symbolic equation, the symbols or formulas of reactants and products are used. The special advantage of the symbolic equation is that it can be balanced to yield a balanced chemical equation as demanded by atomic theory, which happens to help a number of different kinds of chemical arithmetic regarding reactions thanks to Avogadro's theory and the consequent mole concept. Some other examples of special representations used in chemistry are listed here. For the specific rules that should be followed while using these representations, see my book, Understanding Chemistry. Normally, textbooks do not include a thorough list of these rules corresponding to each special representation introduced. Now that we have discussed all four major activities of the scientific process, we now have all the results of these activities. As mentioned at the beginning of part 1 of this video series, these 11 results can be used as a unifying thread to make connections in chemistry. Given their significance, I would like to read these one by one. These are special terms, special representations, experiments, isolated facts, empirical classifications, laws, calculations based on laws, theories, explanations of already known facts using theories, theoretical classifications, and principles. Any thought experiment is designed and the predictions using a corresponding theory are made by scientists, and hence it is not a part of academics unless it is included for historical reasons regarding the evolution of ideas. Therefore, it is not included here. Here is a crucial point to take note of now. What any student comes across in the textbook or in the lecture can be any one of the above 11 results. While reading something in the textbook or hearing something in the lecture, it is extremely beneficial for any student to make it a regular habit of raising the following kind of questions. For example, is this a special term in chemistry? If so, what is its precise definition that ensures I use it correctly and follow others properly? Or is it a special representation that allows concise communication? If so, what are the specific rules to be followed while using it in order to ensure uniform and proper communication? Or is this a law? If so, what is its scope and what are its limitations? What is its mathematical statement, namely the numerical pattern recognized in relevant experimental data? What is its verbal statement? What kind of calculations can be performed using its mathematical equation? Or is it a member of a classification? If so, is it empirical or theoretical? What are the other members of this classification scheme? What basis or set of bases does it use to compare and contrast facts? Or is this an explanation of a fact using a theory? If so, what is that theory? Which postulate or postulates of that theory are used in the explanation? And so on and so forth, covering all 11 results. It is advisable to ask the above questions in one particular systematic sequence every time to ensure no omission or duplication. Whatever is learned, identifying and realizing what exactly it is helps one properly compartmentalize all the learned information in the brain into appropriate compartments. That is, to use the analogy of the chain of links indicated at the beginning of part 1 of this video series, it helps one correctly connect it to the appropriate link in the chain of links formed by using the 11 results of the scientific process. In fact, an effective and efficient method of studying is to compare and contrast all that is learned. The above offers a fantastic framework for that to happen. It ensures no mixing up or confusion occurring later, especially during exams when the brain can easily go on a strike. All of the above, in turn, helps one obtain a deeper perspective into what is all learned in the name of chemistry, make powerful connections among all things learned, and thereby understand chemistry as a whole, since the operational definition of understanding is, as was mentioned at the very beginning of part 1, simply making connections between the new information and the old information already present in the brain. Following this with a periodic review for long enough time allows one to effectively remember everything over a very long period of time, or rather forever, which I can promise from personal experience. In addition, a student may see in the textbook or hear in the lecture any one of the following 4 major learning aids that very much facilitate the learning process. The first one is simple rules or guidelines, which are simply the statements of simple patterns that we recognize when we analyze the given context in detail. Some examples are listed here. These are extremely useful because once we understand the original analysis that led to the recognition of the simple pattern stated in the form of the given rule, then we don't need to repeat that analysis every time, but simply apply the rule and get the desired result soon. But it is essential to understand the analysis first rather than rote learn the rules. Unfortunately, textbooks don't generally discuss such analyses. One can refer to my book, Understanding Chemistry, for the corresponding analyses for all simple rules. A couple of example analyses follow in order for you to understand what is referred to here. Consider the result of a particular measurement, namely 45.62 milliliters. All 4 digits in this number are non-zero digits, and they are all significant as they all come from the apparatus used. The last digit is an estimate of the meniscus position in the space of the smallest subdivision, which is also considered as significant. Therefore, the number of sigfigs is 4. Let us say we convert this unit to different bigger metric units like liter, kiloliter, and megaliter. Let us follow the factor label method discussed in detail in part 2 of this video series for the conversions. As can be seen here, conversion to any bigger metric unit always introduces leading zeros, namely zeros to the left of the first non-zero digit. Are these zeros significant? The answer is a big no, since such a conversion of unit can never ever change the number of sigfigs that is determined by the specific nature of the apparatus used in the measurement process. This simple pattern that's always observed during this kind of analysis is stated as a simple rule for identifying the number of sigfigs in a given number, namely leading zeros are always non-significant. Thus, the number of sigfigs in each of 0.04562 liter, 0.00004562 kiloliter, and 4.562 times 10 raised to negative 8 megaliter is 4. On the other hand, consider the results of 50.8 milliliters, 50.80 milliliters, and 50.800 milliliters obtained with 3 different degrees of precision using different apparatus. The numbers of sigfigs in these numbers are 3, 4, and 5 respectively, since any zeros sandwiched between two non-zero digits and the trailing zeros to the right of the decimal point are always significant as they come from the apparatus or instrument used. Let us say we convert the unit of milliliter in each to the same smaller metric unit, microliter. Again, let us follow the factor label method of unit conversion. As can be seen here, conversion to any smaller metric unit can introduce trailing zeros before the implied decimal point of a whole number. Are these zeros significant? The answer is, it simply depends. In the first case, there are only 3 sigfigs in 50,800 microliters, the same as in the original 50.8 milliliters. Therefore, both trailing zeros are not significant. In the second, there are 4 sigfigs, the same as in 50.80 milliliters. Therefore, the last trailing zero is not significant, but the previous one is. In the third case, there are 5 sigfigs, the same as in 50.800 milliliters. Therefore, both trailing zeros are significant in this case. Thus, we cannot say for sure how many sigfigs there are in the absence of information about the original value. So, the simple rule in this case is it depends, and in the absence of more information about the origin of the number, give a range with the minimum value excluding all the trailing zeros and the maximum value including all the digits. Thus, the number of sigfigs in 50,800 microliters is 3 to 5. It is definitely wrong to give the answer as 5 or 3. The only way to express the correct number of sigfigs in this case is by using the scientific notation such as 5.08 times 10 raised to 4, 5.080 times 10 raised to 4, or 5.0800 times 10 raised to 4 to indicate 3, 4 and 5 sigfigs respectively. The second major learning aid important in chemistry is models. A model in chemistry is any suitable object in the macroscopic world to mimic a theoretical entity or concept in the microscopic world. The main objective of the model is to help us imagine that invisible world. Examples are listed here. The term model is sometimes used as a synonym for theory, as in, for example, Bohr model. Bohr theory is much more than the model referred to by the term Bohr model, because among the 5 postulates of Bohr theory listed here, only the first one implies that Bohr used the planetary system where the planets revolve around the sun in specific orbits as a model or analogy. The model stops right there and has nothing to do with the remaining four postulates. In fact, Bohr invokes quantization of electrons' energy in postulate 2 and of its angular momentum in postulate 3. But these are not quantized for the planets and hence do not apply to them. Therefore, it is not at all appropriate to call the whole of Bohr theory as Bohr model. The third major learning aid is analogies. An example discussed in my book, Understanding Chemistry, helps one relate oneself better to the quantum theory concepts regarding the special representation called electron configuration in atoms. Consider an atom to be analogous to a country like our United States. The shells in the atom are then analogous to the states such as Pennsylvania, etc. The subshells in the shells are analogous to the cities in, for example, Pennsylvania, such as Pittsburgh, Philadelphia, etc. Let us assume that the only buildings present in these cities are various homes. There are no other kinds of buildings such as schools, hospitals, industries, etc. The orbitals in the subshells are analogous to the homes in the cities. And finally, the electrons are analogous to the people living in the homes. The atom is an interesting and a unique country in the sense that a given state can have only a specific number of cities, a given city only a specific number of homes that are either spherical in shape or have specific orientations in space, and finally any home can accommodate only a maximum of 2 people in it, with those being a male and a female analogous to the 2 electrons in an orbital being of opposite spins. It is important to learn the above specific details. To continue the analogy, similar to the home addresses that humans in a given country are associated with, each electron in a given atom is associated with a unique address. Yes, even the 2 in the same home, namely orbital, have 2 different addresses, interestingly enough. One uses 4 different quantum numbers to construct these addresses. According to a corollary of Pauli principle that the electrons are believed to follow as fermion particles, no 2 electrons in the same atom can have the same set of values for the 4 quantum numbers. Therefore, because only the 2 values of plus 1/2 and minus 1/2 are allowed for the spin quantum number, a maximum of only 2 electrons with opposite spins can occupy any orbital, and hence different addresses arise for them. This later statement, which is a special consequence of the Pauli principle, is referred to as the Pauli exclusion principle. Incidentally, Stephen Hawking elegantly emphasizes as follows the practical significance of this principle in his book, A Brief History of Time. If the world had been created without the Pauli exclusion principle, quarks would not form separate, well-defined protons and neutrons, nor would these, together with the electrons, form separate, well-defined atoms. They would all collapse to form a roughly uniform, dense soup. Thus, we humans would not have been there along with the various forms of matter around us but for this principle. Since students in general chemistry are not taught quantum theory, they have no way of understanding the origins of the ideas shown here. The reason they are not taught this theory is that even to read its postulates, let alone understand, one has to know calculus. Therefore, the above analogy becomes extremely helpful for them to remember the essential details regarding electron configurations. The fourth and last major learning aid is mnemonics. A mnemonic is any device that helps one remember and recall any given information at any desired time in the future. The most powerful mnemonic in chemistry is, thanks to Bohr, his long form of the periodic table. He modified Mendeleev's short form to the long form in order for it to parallel the electron configurations of atoms. Therefore, by applying the logic in the reverse direction, one can effectively and efficiently use the periodic table as a mnemonic for recalling electron configurations correctly. The long form is based on which subshell the last distinguishing electron in an atom goes into. Thus, one can separate the periodic table into blocks of atoms or elements. Groups 1A and 2A constitute the S block elements or atoms. The shell number of the S subshell is equal to the period number. Groups 3A through 8A constitute the P block elements in whose atoms the last distinguishing electron goes into the P subshell by following Hund's principle. Again, the shell number of the P subshell is equal to the period number. B groups constitute the D block elements in whose atoms the last distinguishing electron goes into the D subshell whose shell number equals the period number minus 1. In lanthanide and actinide atoms, the last distinguishing electron goes into the 4F and 5F subshells respectively. So, to determine the electron configuration of a given atom, walk along the periodic table from left to right, period by period, paying attention to the block with respect to the subshell and saying or writing down 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, etc. until you hit the given atom, making sure that the sum of the superscripts equals the atomic number of the given atom. Another example of useful mnemonics is shown here. It follows a trick normally followed in designing a mnemonic, namely exploiting the similarity in the first letter. and a couple others are listed here. For yet other helpful mnemonics, see my book, Understanding Chemistry. One should keep in mind that in several ways the mnemonic for a given information can be designed. Whichever the given person is able to relate well to can be the option to choose and use. Adding the above 4 major learning aids to the earlier 11 results of the scientific process yields a total of 15 links in the unifying thread. Whatever new information you read in the text or hear in the lecture, chances are that it will be one of these 15. Be thorough with these 15 and always try to identify any new information you come across with one of these and compartmentalize it in the brain accordingly. In other words, connect it to the corresponding link in the thread. It means you understand it to that extent. Then, of course, keep connecting it to suitable links in other relevant chains, thereby forming very complex chains in the brain and thereby understanding it more and more until your understanding is complete. I thank you all wholeheartedly for watching this video series. My next YouTube video project is an efficient method of working out possible structures and Lewis structures of molecules and molecular ions by making connections to the electron configurations of atoms and monatomic ions.